So Wen is going to present to us on multi-scale modeling of the subsurface using deep learning. Now I want to, you know what, I'm not going to say anything else, because anything else I'll say, I'll be tempted to steal your thunder, because I'm too excited about this work. Wen, please take it away.
Thank you very much, Dr. Hirsch, for the brief introduction. And yeah, thank you everyone for continue to listen to my presentation. So in this section, I'm going to talk about the application of deep learning for multi-scale subsurface models. So to start, we'll start with the brief executive summary. So why it's important to model the multi-scale architectures in our reservoir models? Because it is very important for identifying the flow unit. And also, we can extract the fluid flow at different scales and make sure that they are consistent with our geological concepts at different scales. So therefore, to incorporate those hierarchical structures into our reservoir modeling workflow, we propose a new machine learning-based workflow to calculate those multi-scale architectures and also populate those architectures with our petrophysical properties. And what we found from this study is that compared to the classical reservoir modeling methods, our new workflow can better honor the geological concepts as well as the geophysical interpretations, and provides better parameterization and also the uncertainty models for our subsurface modeling. And also, the proposed multi-scale modeling methods can be used for to solve different inverse problems in our energy exploration projects, like the geophysical inversion or production data history matching. All right, so what are the problems with the classical reservoir modeling method? The first problem I'm going to mention is the problem with multi-scale modeling. So when we're talking about multi-scale modeling, we're actually talking about the hierarchical architectures in our geological sediments, such as in this Lobe deposit on the left. You can see, for example, the largest architectural element in this plot is a Lobe complex, and within it is the Lobe and which is composed with the Lobe elements, and Lobe elements can be further defined by the bed units. So in order to capture those different hierarchies, and also honor the geophysical interpretations, we have to develop methods. We have to develop a method to honor both the depositional hierarchies and the geophysical interpretation. But the current methods, such as the cookie cutter methods, often fail to capture the geophysical or petrophysical interpretation, especially at the boundaries. For example, in this case, where we assume there are two bounding surfaces for the Lobe distribution within it. And when we simulate Lobe distribution and use a cookie cutter approach to fill the area between those bounding surfaces, we can find that there are some artifacts near the boundaries. For example, and here we can see that there is a kind of flow conduits, but that is actually artifacts. And also, as I mentioned, we have to condition our reservoir models to our geophysical or petrophysical interpretations. However, as it shows here, as we go to the more process-based modeling approach, it becomes more difficult to constrain our model with the geophysical or petrophysical interpretation. But as we go further to the geostatistical modeling approach, it becomes more difficult to capture the geological concepts or the multi-scale kind of depositional architectures. So in order to get a both architectural concepts and the data conditioning, we developed a machine learning approach to perform this hierarchical modeling. So the first step is to specify the conditioning data for structural modeling. By structural modeling, I mean the modeling of the bounding surfaces of different architectural elements, below the seismic resolution, such as the boundaries of a lobe or a lobe elements. It depends on the resolution of the seismic. And then after we get those conditioning data, we would calculate the bed unit distribution in the lobe complex unit with the stochastic peaks-to-peaks methods, which is a machine learning approach I presented last year. And then we will use a clustering method to extract the lobe units by segmenting the bed unit distribution. And then we will repeat the step 2 and 3 for the lobe element scale. And finally, after we get the structural modeling, we're going to apply the geostatistical method to calculate the petrophysical property distribution for those architectural elements. So here is a diagram showing the whole workflow. So we'll start with the horizon, like the major horizons identified from the seismic, and also the interpretation, like the zonations or well correlations we got from our well log interpretation. And then we will condition our lobate reservoir model to those data and calculate the bed index. So the bed index increases from the bottom to top of a lobe element. And then from the bed index, we would use a clustering method to get each individual lobe. And then after we get the container, the lobe unit container, we can repeat step 2 and 3 by using the boundaries of the lobe unit as a new conditioning boundaries and generates lobe elements distribution within those each individual lobe. And then we will extract each individual lobe elements. And finally, we would parameterize this whole reservoir by either using the lobe unit or lobe elements, and then stochastically populate the properties with this parameterization. So the first 4 steps are actually for the structural modeling, and the property modeling is only the last step. And by structural, and when we do structural modeling in this way, we are actually forcing our geological model to honor the geological concepts, the hierarchical structures that is commonly, that should be honored in nature. And also we want to incorporate the fine scale correlation information from our well log interpretation into this modeling process, because in classical geostatistical modeling of our reservoir, we don't often consider those fine scale correlations between wells. So by modeling in this hierarchical way, we can force our geological elements to honor these correlations obtained from our well log interpretation. And here are the results I got from this hierarchical modeling workflow. So as I mentioned, we will start with the stochastic lobe unit modeling by constraining it with the horizons from the lobe complex. also the well data. So here are some stochastic model realizations of our Lobe units, which can be identified by the increasing order of our bed units. And also, this is a fence view of these different realizations. As we can see, the correlations of from our well log interpretation are actually honored in this example. And then after we get the bed unit distribution, we will extract each individual lobe by using the clustering method, and then repeat those steps to get the bed unit distribution for lobe elements, and then extract the lobe elements by clustering the bed units and the lobe element scale. In that way, we preserve the geological concepts at different scales. And after we get the architectural, the structural models at different scale, then we can populate our properties with the classical geostatistical methods like the variogram-based or MPS-based approach. For example, in this case, we parameterize our model with the distribution of a lobe unit, and then we can simulate the distribution of shale beds within those lobe unit, and also we can stochastically populate the average porosity or permeability for those different individual lobe units. And then we will go to the lobe element scale, and then the property model at the lobe scale are used as the prior model for the lobe element scale. So in the lobe element scale modeling, we assume that the property distribution of lobe elements within each lobe is stationary, which is actually consistent with the geological concepts as well. And then we will calculate the trend out as well as the average properties for each lobe elements. And finally, we can go to the bed unit scale and populate the properties for each individual bed. And in this way, we preserved and honored the geological concepts at different scales. And also we honor the geophysical and the petrophysical interpretations at different scales. And these are some statistical analysis of how well our machine learning-based approach reproduce the statistics of our training models, which are calculated with the rule-based approach. So this is the spatial probability distribution of our lobe units. As we can see, the upper four figures shows the probability distribution from the rule-based approach, and the figures on the bottom shows the probability distribution from our machine learning based workflow. So as you can see, the probability distribution are very similar to each other. So we can see for sure that the geometry, uncertainties of the geometries of our lobe units are well reproduced. Also, we checked the stacking patterns of our bed units. As we can see, the depositional patterns calculated with the matrix are also well reproduced. Also, this matrix is consistent with the experiment study from previous research. And also, we checked the property distribution and reproduction. So as we can see, the porosity distribution from the model realization set, the truth models are matched. Also, the net to gross from the truth model set, the model realizations are also matched. We also checked the dynamic properties, the uncertainties of our dynamic properties reproduction. As we can see, the streamlines and the dynamic Lorentz coefficients from the truth model and the model realizations are very similar. which indicates that our machine learning-based approach reproduce uncertain models for those dynamic properties. As for application, we have used this multi-scale reservoir modeling approach to parameterize our reservoir models that use it as a model reduction approach to perform the multi-scale history matching projects. So I will not go into very detail of how we perform this multi-scale history matching due to the limit of time. But the basic idea is to start with large-scale reservoir model and try to match the production data, and then use them as prior model and simulate the next scale reservoir models using those prior models. And then we have more model parameters, and then we perform the history matching again to try to get a better match of our production data. And we will only model at the scale where the production data are well matched, and then we will not further refine our reservoir models. And by doing that, we will avoid overfitting our reservoir model to the sedimentary architectures that do not affect the fluid flow very much. So this is the kind of the reservoir models we use at the Lobe scale. So we basically first history matching with our Lobe scale model, and after we get a fair match, we will use this model as a prior and calculate the Lobe element scale to get a better match of our production data. And this is the uncertain models of our prior model for the Lobe element scale modeling. And after we get the prior models from the Lobe element scale history matching, we will use it as the prior to get the Lobe element model constructed. So this is the results after I performed the Lobe element scale reservoir modeling and history matching. As you can see, the uncertainties are well captured with this approach. And these are different realizations of Lobe element scale reservoir modeling. As you can see, we didn't try to simulate the bed scale heterogeneity because we've already got a very good match of our production data. So in this way, we avoid kind of make our reservoir model too complicated, and also only capture the geological features that are affecting our fluid flow. So to summarize our work, we can now use our machine learning-based workflow to perform the true multi-scale subsurface modeling while honor the geophysical and petrophysical interpretation. And by parameterizing our reservoir model with those geologically consistent architectural elements, we can better reproduce the fluid flow behaviors of our reservoir. And by incorporating all those geological information into our reservoir modeling and history matching process, we're expecting to see a better subsurface decision making. And in the future, we're going to check if the model variability of our training models are reproduced by our machine learning based models. Also, we will check if a more complex, the features from more complex training models can be reproduced by our machine learning based approach, such as combinations of different depositional environments. And last, I would again like to thank all of our sponsors for supporting our studies. So please feel free to ask me any questions you have.
Awesome, Win. Thank you very much. Another excellent presentation. I appreciate that. Now, this work, let me just make a couple of comments. I didn't want to steal your thunder while you're talking before you talked, Wen, but just imagine, to me, this is one of the first approaches where we can truly do multi-scale subsurface modeling. If you look at the standard geostatistical workflows, it doesn't matter if you're looking at like FluVsim and some of that hierarchical modeling done by Tom Tran and Clayton Deutsch. Great work with all their transformations and so forth. At the end of the day, it was a cookie cutter approach. One scale doesn't understand what the other scale is doing. There's important information between the scales, and when you've shown how important it is to incorporate that. Now you get extra marks for the fact that you went into the rigor of checking your models, which we would expect for production models in the subsurface, to make sure there's no bias, to make sure you reproduce the spatial structures and stacking patterns. And you did fit for purpose modeling where you said, nope, I made multi-scale, but I'm going to stop here. That's enough. I'm not going to overfit. So Wen, excellent work. Appreciate all of that. Any questions or comments from anyone here? Any questions? I didn't see anything in the chat window. How's your energy level? I do that with my students all the time. All right. The code is available, papers available, documentation. People can try this out, check it out. This is very powerful methodologies.